What I thought we'd do today is to push on with this celestial sphere stuff, okay? Last time we went through what I call geography. That's completely the wrong word, I know. The geography of the celestial sphere, what goes where, and etc., etc. The coordinate system, right ascension, declination, all that business. And what I want to do today is to push on from that and have a look at what the celestial sphere looks like from inside, okay? So that's our theme for today, if you like, is what the celestial sphere looks like from inside. Okay? So let's just jump there. Okay. Last time we drew what I always call the God's eye view, which is the view from outside the celestial sphere, which is a bit mad really. So as I draw this up, hopefully this is familiar from last time. North celestial pole at the top, south celestial pole at the bottom, and the celestial equator around the middle. It's not too surprising. Okay. All of these are just projections of the Earth's equator and poles. Okay, they're just, you can imagine them pushed out into space like that, then you'd have the right idea. Okay, that's called the celestial sphere. Those are its bits, and I won't draw it all over again, but you should be able to remember how to work out or to find those two coordinates. Okay, the celestial equivalent of longitude and latitude is right ascension and declination. Okay, declination is angle up from the equator or angle down from the equator, plus or minus, and right ascension, you remember, from the first point of Aries is number of hours round. Okay. Now the other thing we did last time was we thought about the fact that the Earth basically gets in the way. Okay. The celestial sphere and its bits is quite interesting, but more interesting is what does it look like from inside? What's the effect of us not looking at it from out here, but actually looking at it from a position 54 degrees above the equator on the Earth? Okay, so there's my little person in Skipton, and because of the Earth, they basically, although I've drawn a very big Earth, in theory the Earth is infinitely small, isn't it? Because the celestial sphere is infinitely big, so I've drawn quite a big Earth, but in principle you can see that there's, at the moment anyway, this half of the celestial sphere is going to be invisible. Okay? As time ticks on, the best way to imagine it, I think, is to imagine this horizon, which is what we call the edge of this blockage. So the top of the bit where the Earth blocks our view, we call the horizon. This horizon is going to, a bit like a coin on a table, is going to spin round, and although I can't see something here at the moment, in 12 hours' time, it'll be visible in my sky. Okay, so this line around here is called your horizon. Okay, now what we need to do now is try and imagine what it would be like looking from that person's view. Okay, and obviously they would have around them a horizon. Okay, and there are a number of important points which we need to identify. The first one is this line here, up through the North Celestial Pole and down to their south point. So that's your north point on your horizon. Okay. If you remember, never eat shredded wheat, that's your easterly point, and that's your westerly point over there, and your southerly point of your horizon is down there. Okay. Now, several ways of going about this, but one way I always think is to identify a couple of very important right angles. Okay. Firstly, there is a very important right angle between the North Celestial Pole and the celestial equator. All right. If I hadn't put the horizon in, this would be even more obvious, but the equator and the pole, just like think about the equator and the pole on the Earth, they're at 90 degrees. Okay. So that angle in there is a right angle. Okay. Now, to do any of this stuff, we need to know, obviously, this angle, which is how tilted is your horizon. Okay. We talked about this last time, and whenever I draw this diagram, it's very confusing because I put this person in a sort of a middle latitude. They could be around 30, 40, 50 degrees latitude, and I've drawn the horizon quite roughly. This angle in here, we mentioned it last time, is not equal to your latitude. The fact that you have a latitude means that you have a tilted horizon. Okay? Where would you have to go on the Earth to have a completely horizontal horizon? Be the North Pole. If you can imagine a little person standing on the top of the Earth, their horizon would be like that. They would have a latitude of 90 degrees, and the tilt of their horizon would be 0. Okay? What would the horizon, this plate here, what would it look like if I stood on the equator? It'd be 90 degrees, wouldn't it? If you imagine somebody standing on the equator, they're basically standing like that, their horizon would be completely vertical, all right? So can I remind you from last time, this angle here, which is the tilt of your horizon, is equal to your... The bit to underline is that bit. It's not your latitude. If I'd said to you that's 54 degrees because Skipton has a latitude of 54 degrees, you've gone, well, his drawing's normally pretty rubbish. Yeah, okay, that's 54. It's not. It's 36. Okay? So here we are in Skipton with a latitude of 54 degrees north. And that's why I'm attempting to draw the celestial sphere 4. What that means is your horizon will be tilted at 36 degrees. Okay? Very, very important. The tilt of your horizon, which is going to define all of this stuff that follows on. Everything we're going to do today depends on you getting the right angle for your horizon. It's not your latitude, it's your co-latitude. Okay? It's 90 minus your latitude, like sine and cosine. It's going to give you 36 degrees. So this angle here is 36 degrees or your latitude. Okay? Now, the horizon is going to spin round, but there are a number of things that just don't change. Okay? And if we bear in mind that's a right angle, okay, then would anyone like to tell me about that angle? Can you see that right angle? Yeah? That angle there to that angle there is again a right angle, all right? The celestial equator and the pole are 90 degrees from each other, okay? So look at this right angle. Now what have we just said? We said this bit is 36. For a latitude of 54, this is your co-latitude of 36. Can you see this is the other bit of the right angle? So if that's 36, that has to be, do you see, 54. Well, let's go back to our horizon. Let's imagine we're looking north, as we are. What would that look like in the sky? What would you be looking between to see that angle? I know it's 54 degrees, but let's park that for a moment. What 2 points would you look between in the sky to see that angle? Yeah, we're lucky in the northern hemisphere because we have a bright star at the North Celestial Pole, don't we? This is more difficult in the southern hemisphere. You've got a bright star almost exactly on the North Celestial Pole that we call Polaris. And this here, this line here is of course your horizon. So here's our first astounding fact, which is, what do you think we call that angle above the horizon? It's altitude, isn't it? All right. So first key fact you need to know about living inside the celestial sphere as we do is that the altitude of Polaris will be equal to your latitude. All right. So important fact you need to know for the exam. The altitude of Polaris is equal to your latitude. That's why I can always point at Polaris. Because also, which direction is it always in? It's always north, isn't it? So this is how, one aspect of how you travel by the stars or navigate by the stars. Wherever you are on the Earth, if you can see Polaris, all you need to measure is its angle above the horizon, and that's equal to your latitude. So imagine we weren't here in Skipton knowing where we are. If we're bobbing about in the mid-Atlantic and we've got no idea where we are, we can measure our latitude using Polaris if we want to. Okay? The height of Polaris above the horizon, in degrees in astronomy, we don't mean meters or kilometers, we mean its angle, okay? The altitude of Polaris is equal to your latitude. So Polaris is always, if this is our horizon view, in Skipton anyway, 54 degrees. That's why I can always do that. And I'm always pointing at Polaris. It's always 54 degrees above the northern horizon, which is over there. Okay? So that's the first one. Is everybody happy with that? Now, the other end of this right angle business in the middle, the other end of this bit here, or this right angle if you like, is this angle here. Okay. Now that's going to involve you looking at your southern horizon. Okay. And looking at this line here, if you can imagine this line here that goes right from your north to your southern horizon. I really can't draw that very well on the other diagrams, but it's known as your meridian. Generally on a sphere, any line that goes from the North Pole to the South Pole is called the meridian. Okay? You'll be familiar with the one that goes from the North Pole through Greenwich to the South Pole. And that's called it's now called the prime meridian, isn't it? Or the Greenwich meridian. Okay? But everybody has their own meridian. Can you imagine on the Earth, there's actually an infinite number, aren't there? If that's the Earth. If you're stood here in Skipton, that's your meridian, okay? It's a couple of degrees west of prime meridian, and hundreds of years ago when these sort of things were still being argued about, there was another meridian that went through Paris and one that went through somewhere in Spain perhaps, and you can have any meridian you like, okay? So when you're observing the night sky, you've always got your own meridian. It's a very simple idea, it's your north-south. So if I start at my northern horizon, I go up through Polaris and then go right over my head down to the southern horizon. That line's called my meridian. Where does it appear on this diagram? It's kind of in squashed flat because it's a 2D diagram. It's that there. Okay? Tell me about this angle. Either tell me how big it is for someone in Skipton with a latitude of 54, or tell me what it is in the sky. So either what would I be looking at to see that angle, or what number of degrees would it be? I think it's going to be, can you see that's 180? Yeah. North horizon to southern horizon is 180. Can you see that 180? Take that right angle out of it. Do you see? You've got 180 degrees there, haven't you? With a right angle in the middle. So what must these two angles add up to? 90. They've got to add up to 90, so I'm afraid that one is your co-latitude. My diagram is deliberately on purpose. I could draw these really well actually, but I do them on purpose really, really badly. So you have to work it out. You can't just look at it. You're absolutely right. It does look like 54, but it's not. Okay? Can I convince you then that must be 36? Because look at this 180 degree line. North horizon, south horizon is 180. There's 90 of it. To make up the other 90 from 54, that would be 36. But what is it? What is that angle in the sky that equals 36 in Skipton? So second important fact is the altitude of the celestial equator on your meridian, your southern meridian, is equal to your co-latitude, which I can't spell. Okay? The way to remember these two, I think, is that right angle. Do you see? North to south is your meridian, okay? And that's going to give you 180 degrees from your north of your horizon to the south of your horizon, okay? In the middle of that 180 degrees, there is a great big right angle. Imagine a giant set square just plonked on top of you. There's a giant right angle in the middle there, which is the angle between the pole and the equator. And that leaves you with this angle here, which is the altitude of the pole star, and that's equal to your latitude. And you have this angle here, which is equal to your co-latitude, which is the altitude of the celestial equator on your meridian. Okay? So if you look south, 36 degrees, the celestial equator, can you imagine like a line through the sky? Where the celestial equator crosses your meridian will be 36 degrees above the horizon. Okay? And that's going to stay the same, I think you can see, as the whole thing goes round. This is actually quite a complicated system. If I say to you, here's a star with these coordinates, where will it be next Tuesday? That's actually very complicated. That's well beyond GCSE astronomy to work out. All right? So what we're picking out here is things that don't change. Do you see, as I spin this thing round, I'm not going to change either of those things. Okay? And there's one more thing which stays the same all the time. So in a way, what we're doing is pulling out the things that don't change as the horizon goes round. Altitude of the pole star, altitude of the equator, and the third one is related to this, and this is where the line diagram gets completely bonkers, the point above your head. Don't confuse this with the celestial equator. Sorry, start again. Don't confuse this with the North Celestial Pole. These 2 points are only the same when you're stood at the North Pole. Can you imagine staying at the North Pole? Above you is the North Celestial Pole, Polaris. Okay? It has an altitude of 90 degrees because you have a latitude of 90 degrees. Okay. Now, tell me about that point there. It's tricky, isn't it? This is your zenith, yeah. Let's do the name first, thank you. It's called your zenith, okay, which means the highest point, as you sometimes hear. It's used in everyday speaking, isn't it? Anyone know the opposite? It's pretty useless, and we never use it much in astronomy. It's a rather grand name. It's called your nadir. It's quite good for insulting people. You sometimes said, there was some political programme on a few years ago, I remember, and somebody said, under David Cameron we've reached the nadir of success or something. Everybody went, oh, well, that sounds really bad. Went home and looked it up. But it means the lowest point. The zenith, can you imagine like the stocks and shares of a company? They reach their zenith is their highest point and their nadir is their lowest point. So, good word for Scrabble. What's going to happen under your zenith? Well, can you imagine the sphere rotating? That angle there is, if you pick a star on your zenith, what's its declination? Well, if I said to you, right, there's a big bright star up there, really exciting, let's try and find out what it is. We'd measure the angle from there to the celestial equator. You with me? What do you call angle up from the celestial equator? Declination. So that angle there is the declination of a star at your zenith. Let me take that out. It's because I've drawn too many lines on the thing. If you had the Earth, that's a good way to think about it. There's Skipton. Here we are standing at Skipton. How many degrees are we above the equator? 54. So if this was a geography diagram, there's the equator, there's the North and South Pole. Here we are in Skipton, we're 54 degrees. Do you get it? Above the equator, that means we've got a latitude of 54 degrees. Let's project that out onto the celestial equator. Sorry, start again, the celestial sphere. Up here, North Celestial Pole. Here, celestial equator. What would this point be? Zenith. That'd be your zenith, wouldn't it? And what would we call this angle? We'd call it the declination of the star at your zenith, wouldn't we? All right? So that's a good way to think about it. That angle there is the declination of a star above your head. Okay? It won't be the same star all the time. You with me? So if you go out tonight, lie in the field, look directly above your head, you'll see all it is a bright star. Yeah? It will drift off a bit later on. Another one will come along. But they will all be stars. Can you imagine this circle? They're all stars which have what is it? It's 54, isn't it? Here's the line of stars that has a declination of 54 degrees. Do you see? That line there, like a little skull cap on top of the thing, that line there is the line of stars. That one's got a declination of 54. Here's another star with a declination of 54. Here's another star with a declination of 54. They're only above your head one at a time, but if you sat and watched all night long, can you imagine? You'd see some blank sky in between, you'd see stars going over, and they all have a declination of equal to your latitude. Okay? But a good way to think about it, absolutely right, let's simplify the diagram, is to imagine your latitude on the Earth and the declination of your zenith on the celestial sphere is actually the same angle. You're measuring the angle between the equator and your position, latitude, or the celestial equator and your zenith, which is what we call its declination. Okay? So our third key fact is the declination of your zenith is equal to your latitude. Okay? These facts you must learn. Okay? These facts you have to learn, and you'll be asked to do things involving them. Okay? So basically, if you imagine going outside, I always think these two are kind of paired up. These two are kind of paired up because they're as a result of the giant set square in the sky. Because of this great big right angle in the middle of your sky, you're left with the altitude of Polaris on your north horizon, equal to your latitude, and the altitude of the celestial equator, where it crosses your meridian on the south, is equal to your co-latitude. Why? Because those two are the other right angle for that one. Okay? The third one, as I say, is basically saying latitude and declination are essentially the same angle. All right? Latitude on the Earth, but projected out, you've got declination. Okay? Is everybody, I know the diagram looks complete dog's breakfast now, but I've drawn too many things. In the handout, it doesn't one at a time. Do you follow? If you struggle to follow this diagram or draw it, if you look in the handout, it's actually got them drawn separately. Okay, it's because I can be able to redraw it each time.